going to talk about in this video a different model, also related to physics, and we talk about it in considerable detail in mechanics of solids and fluids. But simple harmonic motion is one of the simplest models that uses differential equations and can be expressed pretty simply in terms of the part and the families of solutions that we're talking about. And it comes up in a very interesting application, which you can generalize to actually a very broad variety of natural phenomena. But if you think about the motion of a spring mass system, where you have some mass, so a block maybe of mass m, attached to a spring with a spring constant k, and it's just attached to a wall, right? Then the spring has a natural length, which we'll call that position x equals 0. And we can either compress or extend the block to beyond its natural length. We've seen this a little bit already before. We talked about in section 6.4 work. It takes work to pull a spring to a beyond its natural length. I don't know, let's call this 10. Similarly, we can compress the spring to below its natural length, so -2, right? So the spring, though, wants to return to its natural length, right? It wants to come back. So that's what we call the restoring force. So Hooke's law is a statement about that restoring force that brings it back to its equilibrium, where that force is equal to -kx. So it's proportional to the distance away from the equilibrium, okay? And k is the spring constant, okay? So spring constant, and x is position relative to equilibrium. So it wants to be in its natural length, and then that measures how far away you are from your natural length. So that means that by Newton's second law, oops, that's not how you spell Newton. We have mx double prime equals -kx, or mx double prime plus kx equals 0, okay? And sometimes we'll write it as x double prime plus k over mx equals 0. And this constant right here, we might also write as omega squared equals k over m, or omega equals the square root of k over m. Omega comes up in that when we write the solution, we'll want to write it in terms of omega. Notice that this equation right here, or represented in any form, is a linear second order dE. We do not get to see how the sausage is made with this one, but stick around I don't know that you'll see it in Math 402, but you'll definitely see it in Math 420. So the solutions, though, solution family has the form x of t. So this is a function of time, right? When you release it from wherever it is, it will oscillate back and forth until it reaches equilibrium, or it may not ever reach equilibrium. In this simple harmonic motion model, it will just keep bouncing back and forth because it'll bounce from one side to the other, We're assuming that there's no air resistance, friction, any of that. So C1 cosine of omega t plus C2 sine of omega t. So this omega is the same omega that I wrote here. And C1 and C2 are the two constants, coefficients that determine the particular solution. Okay. All right. So how do we know that this is true? Well, I'm claiming that this is what these solutions look like, right? Which are sinusoids ultimately. But how? How could this be the case, right? So let's do an example. I'm going to verify that x of t equals C1 cosine of 5/2 t plus C2 sine of 5/2 t is a family of solutions for the differential equation for x double prime plus 25x equals 0. So what would this come from? This would come from, it could model a spring mass system where we have a mass that is 4 kilograms and 25 is the spring constant, right? So how do we verify that this is true? That this function or family of functions satisfies this differential equation? Well, we're going to have to find the derivatives of x. So we have x of t. So x has been given to us with two unknowns, but that shouldn't be a problem. When we derive, right? So remember to carefully use your derivative rules. 5/2 c1 sine of 5/2 t plus 5/2 c2 cosine of 5/2 t. And then x double prime is negative 25 over 4 c1 cosine of 5/2 t minus 25 over 4 c2 sine of 5/2 t. Okay. Very interestingly, okay, notice that if we factor out, so this is the original, the first derivative, this is the second derivative. If we factor out a negative 25 over 4, we get c1 cosine of 5/2 t plus c2 sine of 5/2 t. Okay, which means that whole thing is x, right? So there's a relationship here, a natural relationship between the acceleration, which is x double prime, and x. And we don't need too much accounting to finally verify that this relationship, right, is exactly what we're looking for, just written slightly different, right? So, in other words, if we replace the left-hand side of that differential equation, so 4x double prime plus 25x, if we replace what we know about x double prime and x in here, do we get 0? Well, let's try it. So 4 times negative 25 over 4x plus 25x. You can see, right? Minus 25x plus 25x. 0. Yeah. It checks out. So it is a solution. Perfect. Okay, so remember, this corresponds to a spring mass system with a mass of 4 kilograms, and our K, the spring constant, is 25 newtons per meter. Okay. And omega, I can talk about it now. Omega, which is 5/2, has the units radian per second because it is the angular velocity of oscillation. Pretty cool, huh? Okay, so to see how this works, right? Let's think about putting these pieces together. So first of all, we're going to do another example. So for a spring mass system, with omega equals 5/2 radian per second, solve the initial value problem with, okay, so remember, our initial value problem has two statements. So we solve the dE that we're interested in, which is, of course, we already have 4x double prime plus 25x equals 0. And subject to, here we're going to have, if this is an initial value problem with two constants that need to be solved, then we have two conditions. So x of 0 equals 1 and x prime of 0 equals 1. How we want to interpret this is the initial position is stretched 1 meter, and the initial velocity is compressing 1 meter per second. So we're stretching and we're compressing, right? In other words, we want to think about the spring mass system as it's starting from a stretched position, right? So its natural tendency is to want to pull back to this is the equilibrium point, right? So it wants to come back to the equilibrium point. Also, we're giving it a nice little shove at the beginning, right? Of 1 meter per second. So both of these two things combined should give us something interesting. Okay, so how do we solve this IVP? So we know the general solution. Our task now is to solve for C1 and C2. So we will use x naught equals 1 and x prime of 0 equals -1 to find C1 and C2. This gives us simultaneous equations. Sometimes it may give us a linear system that we need to solve using linear system methods. Sometimes it's easier, okay? So let's use that first condition. So first, x of 0 equals 1 is going to give us 1 equals C1 times cosine of 0 plus C2 times sine of 0. Okay, cool thing here is that sine of 0 is eliminated. So the whole second term in this equation becomes 0. And then cosine of 0 is 1. So we get C1 times 1 equals 1. So C1 equals 1. Okay, that's nice. That means that we can use that for the next equation. So x prime of 0 equals -1. Equivalently then, -1 equals, remember that this time we're working with the velocity, so the derivative. -5/2 C1 sine of 0 plus 5/2 C2 cosine of 0. Now, in this equation, the first term cancels out. So we just get -1 equals 5/2 C2 times 1, which gives us C2 equals -2/5. So finally, x of t equals cosine of 5/2t minus 2/5 sine of 5/2 t. And just to show you what that looks like, right? Let's actually go to the, let's go to Desmos real quick. Okay, so let's actually, you know, find out what that looks like. Cosine of 5/2 is 2.5, by the way. So 2.5. I'm going to use the variable x here, just because that's the natural variable here. But just know that that is the same. So 2/5 though is 0.4 times, should we use 0.4, times sine of 2.5x. Okay. Now, all of these, because they have the same angular velocity, can be expressed as a single sinusoid. But that's beyond the scope of this course, and we won't talk about it in any detail. But roughly then you can think about this is a shifted sine wave, where you can see that at t equals 0, right, we're starting from this, not the full peak, but just shy of the peak position, right? And then we are being pushed toward in the negative direction to reach a maximum that represents compression, and then we were oscillating all the way back to the peak, which is expansion, right? So what it looks like then is that based on the particular initial value, we are not starting from like its maximum length. So remember that this is the picture of the spring mass system, but the maximum is probably somewhere like here. Maybe this is the maximum, right? So it's going to be oscillating back and forth between those two. So it'll look like this. The trajectory that it traces out looks like this. So it'll cross the equilibrium point, go back down to compression, cross the equilibrium point again, come back to its full stretched out form, back to equilibrium, full compression, back to equilibrium, and so on and so forth, forever. Forever. Yeah, isn't that crazy? Right, so simple harmonic motion. Isn't that cool? So we just found the particular solution to that IVP. And you can actually glean a lot of really cool and interesting ideas from this. Yeah, so, but that concludes that. We're going to move on to the next section in the next video.